Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. However you guys are right? Wow. Hopefully we are always physically and spiritually healthy friends. Okay, on this occasion, introduce us from group 12. We will show a video about circle. Okay, for the first video starting from me, so introduce my name is Sapriadi.
Okay, I'm Febrianti Khoirunnisa, as the second speaker.
Hi everyone, I am Nurul Khaerani as third speaker.
Now, happy waiting. Okay, for the first video starting from me, so introduce my name is Sapriadi. I will discuss about the basic and examples of the cycle. Now, happy waiting.
Okay, so now I will present. The first is circles and related segments and angles. A circle is a locus of points that lie in a plane, and all of these points are a certain and equidistant distance from a certain point. The particular point is called the center of the circle, and the specific distance is called the length of the radius or radius of the circle. The name of the circle depends on the name of the center point. Okay, the next is the terms in a circle. The first is radius. Radius is a line segment joining the center and any point on the circle, and you can see in the picture. The second is arc. Arc is a part of the circle. You can see in the picture. The third is a curve. A curve is a line that joins any two points on a circle, and you can see in the picture. The fourth is diameter. Diameter is the curve that passes through the center of the circle. The diameter is the longest curve and the length is twice the radius, and you can see in the picture. The fifth is a bottom. A bottom is a line drawn from the center of a circle perpendicular to the core of the circle, and you can see in the picture. The sixth is sector. Sector is area bound by two radii and arc of a circle, and you can see in the picture. The seventh is tangent. Tangent is a line that intersects the circle at exactly one point, and you can see in the picture. The eighth is circumference of the circle. Circumference of the circle is the length of the arc forming the circle, and you can see in the picture. The ninth is area of a circle. Area of a circle is the area of the flat area bounded by the circle, and you can see in the picture. And the last is segment. Segment is the area bound by the core and arc of a circle, and you can see in the picture. Okay, the next for figure 6.1, a circle is named by its center point. In figure 6.1, point P is the center of the circle. The symbol for a circle is P, so the circle in figure 6.1 is called circle P. Points A, B, C, and D are points at the circle. Point R is inside the circle P. Points G and H are outside the circle P. Okay, the next for figure 6.2. In figure 6.2, SQ is the radius of the circle Q. SQ, TQ, PQ, WQ are radii or plural radius of the circle Q. By definition, SQ is TQ is PQ is WQ. Or radii of circles are congruent. A line segment connecting two points of a circle, such as SW in figure 6.2, is a curve. The diameter of a circle is twice the length of the radius. TW in figure 6.2 is the diameter. Okay, the next, congruent circles. Congruent circles are two or more circles that have congruent radii, and you can see in the figure 6.3. In figure 6.3, circles P and Q are congruent because their radii are the same length. And the next, concentric circles. Concentric circles are coplanar circles that have the same center, and you can see in the figure 6.4. The concentric circles in figure 6.4 have a common center O. Okay, you can see in figure 6.5. In figure 6.5, the circumference shown from point A to point B is RAB, denoted by AB. If AC is diameter, then ABC, three letters choose for clarity, is a semicircle. In figure 6.5, minor arcs like AB is part of semicircle. Main arcs such as ABCD also denote ABD, which or ACD is more than a half circle but less than the whole circle. Next is the angle at the center of a circle. The angle at the center of a circle is an angle whose vertex is the center of the circle and whose angle is the angle at the center of the circle, whose side is the radius of the circle. And you can see in the figure 6.6. In figure 6.6, the angle NOP is the center angle of the circle O. The intercept arc from the angle NOP is NP. The arc that is cut from an angle is determined by the 2 points of intersection of the angle with the circle and all the points of the arc on the inside of the angle. Okay, to clearly in figure 6.6, so you can see in the example 1. In the figure 6.6, NP and NQ intersects at O, the center of the circle. So the question is shown already. And in the figure 6.6, you can see already is OM, OQ, OP, and ON. Okay, the second is both diameters. And you can see in the figure 6.6, we know diameters is MP and QN. The next shown all four chords. And in the figure 6.6, we can see the chords is MP, QN, QP, and NP. The next one middle central angle, and you can see in the figure 6.6, we can see the middle or central angle is the Greek angle QOP. The next one smaller bow or minor arch, and in the figure 6.6, we can see or we can know that smaller bow is NP. The next is one semicircle, and in the figure 6.6, one semicircle is MQP. Okay, the next is one major arch, and you can see in the figure 6.6, the major arch is MQN. Okay, the next is bow intercept from angle MON, and you can see in the figure 6.6, the bow intercept from angle MON is MN, and the last is middle angle that intersects NP, and you can see in the figure 6.6, the middle angle that intersects NP is angle NOP. Okay, the next, the theorem 6.1.1. The theorem 6.1.1 is the radius perpendicular to the curve bisects the curve. Given OD is perpendicular to AB in the cycle, you can see the figure 6.7. So prove the OD divides by 2AB. To proving the given or the from the figure 6.7, OD is perpendicular to AB in a circle, image of OA and OB radius. Now OA congruent OB because all the radii of the circle are congruent, since angle 1 and 2 are true, angles and OC congruent OC. We see angle OCA congruent angle OCB with HL, then with AC congruent CB by CPCTC, so OD divides AB by 2. Okay, the next is relationship of angle and arch in a circle, and you can see in the figure 6.8. In figure 6.8, the number of angular steps about the point O, the angle is determined by the perpendicular diameters AC and AD is 360 degrees. Similarly, a circle can be separated into 360 equal arcs, each measuring 1 degree the size of the arch. That is, each arch will be intercepted by a central angle measuring 1 degree. Okay, the next is the sum of the measures of successive arcs that make up a circle is 360 degree. Okay, you can see in the figure 6.9. In circle Y, in the figure 6.9, in point A, if M angle XYZ equals 76 degree, then with middle angle postulate, if two arcs have the same degree measure in the figure 6.9, point B and C, but are part of two circles with unequal radii, then these arcs will not coincide. This observation leads to the following definition. So from the definition is, in a congruent circle or circles, congruent arcs are arcs of the same size. And you can see in the figure 6.10, to clarify the definition of congruent arcs, consider the concentric circles are having the same center in figure 6.10. Here the degree measures of the angle AOB of the smaller circle is equal to the measures of the degree of the larger circle, whereas measures of arch AB is measure of arch CD. So AB is not equal CD because the arcs will not coincide.
I'm Febrianti Khoirunnisa as the second speaker, and I will continue the explanation from the first speaker and enter in the next material, that material 6.2 about more angle measure in the side.
As we have seen, the measure of an arc can be used to measure the corresponding central angle. The measure of an arc can also be used to measure other types of angles related to the circle, including the inscribed angle. Definition: an inscribed angle of a circle is an angle whose vertex is a point on the circle and whose sides are chords of the circle. The word inscribed is often linked to the word inside, as suggested by the discovered activity at the left. The relationship between the measure of inscribed angle and its intercept arc is true in general, like the feature. Theorem 6.1.2. The measure of an inscribed angle of circle is 1/2 the measure of intercept arc. The proof of Theorem 6.1.2 must be divided into 3 cases. Case 1. One side of the inscribed angle is a diameter. From the figure, proof of case 1, we begin by constructing radius line segment RO, then M angle ROT equals to M R arc RT, because the central angle has a measure equal to the measure of its intercept arc. With line segment OR congruent line segment OS. Triangle ROS is isosceles and angle R equals to M angle S. Now, the exterior angle of the triangle is angle ROT. So, M angle ROT equals to M angle R plus M angle S. Because M angle R equals to M angle S, M angle ROT equals to 2 times M angle S. Then M angle S equals to half M angle or ROT with M angle ROT equals to M arc RT. We have M angle S equals to half M arc RT by substitution. As to the diameter to the vertex of the inscribed angle lies in the interior of the angle. Case 3. The diameter to the vertex of the inscribed angle lies in the exterior of angle. And see the figure. Theorem 6.1.3. In a circle or incongruent circle, congruent minor arcs have congruent central angles. From the figure, if arc AB congruent arc CD in congruent circles O and P, then angle 1 congruent angle 2 by Theorem 6.1.3. We suggest that the student make drawings to illustrate each of the next 3 theorems. Some of the proofs depend on auxiliary reading. Theorem 6.1.4. In circle or congruent circle, congruent central angle have congruent arcs. And the Theorem 6.1.5. In a circle or incongruent circles, congruent chords have congruent minor arcs. In Theorem 6.1.6, in a circle or incongruent circles, congruent arcs have congruent chords. On the basis of an earlier definition, we define the distance from the center of a circle to a chord to be the length of the perpendicular segment joining the center to the chords. Congruent triangles are used to prove the next 2 theorems. Theorem 6.1.7. Chords that are at the same distance from the center of a circle are congruent. For the proof, from the figure, given line segment OA, perpendicular line segment CD, and line segment OB, perpendicular line segment EF. Segment OB, perpendicular line segment EF in central point O. See the figure 6.18. Line segment OA equals to line segment OB. We must prove line segment CD equals line segment EF. For proving, draw ready line segment OC and line segment OE with line segment OA perpendicular line segment CD and line segment OB perpendicular line segment EF. Angle OAC and angle OBE are right angle S. Line segment OA equals to line segment OB is given, and line segment OC equals to line segment OE because all radii of a circle are congruent. Triangle OAC and triangle OBE are right triangles. Thus, triangle OAC equals to triangle OBE by HL. By CPCTC, line segment CA equals to line segment BE, so CA equals to BE. Then 2 times CA equals to 2 times BE, but 2 times CA equals to CD because A is the midpoint of chords line segment CD. Line segment OA bisects chords line segment CD because line segment OA is part of radius. See the Theorem 6.1.1. Likewise, 2 times BE equals to EF, and it follows that CD equals to EF and line segment CD congruent line segment EF. Proves the remaining theorems are left as exercise. Theorem 6.1.8. Congruent chords are located at the same distance from the center of a circle. From the figure in circle O, the two chords AB and CD are congruent, that they are equidistant from the point O. Theorem 6.1.9. An angle inscribed in a semicircle is a right angle. Theorem 6.1.9 is illustrated in figure 6.19, where angle S is inscribed in the semicircle arc RST. Note that angle S also intercepts a semicircle arc RVT. Theorem 6.1.10. If two inscribed angles intercept the same arc, then these angles are congruent. Theorem 6.1.10 is illustrated in the figure 6.20. Note that angle A and angle 2 both intercept arc XY because M angle 1 equals to half M arc XY and angle 2 equals to half M arc XY. So angle 1 congruent angle 2. Now we enter in the material 6.2 about more angle measured in the circle. We begin this section by considering lines, rays, and segments that are related to the circle. We assume that the lines and circle are coplanar. Definition: a tangent is a line that intersects a circle at exactly one point. The point of intersection is the point of contact or point of tangency. The term tangent also applies to a segment or ray that is part of a tangent line to a circle. In each case, the tangent touches the circle at one point. Definition: a secant is a line or segment or ray that intersects a circle at exactly 2 points. From the figure A, line S is a secant to central point O. Also, line T is a tangent to central point O, and point C is its point of contact. In the figure B, line segment AB is tangent to central point Q, and point T is its point of tangency. Line segment CD is secant with points of intersection at E and F. Definition: a polygon is inscribed in a circle if its vertices are points on the circle and its sides are chords of the circle. Equivalently, the circle is sides to be circumscribed about the polygon. The polygon inscribed in a circle is further described as a cyclic polygon. Triangle ABC is inscribed in central point O, and quadrilateral RSTV is inscribed in central point Q. Conversely, central point O is circumscribed about triangle ABC, and central point Q is circumscribed about quadrilateral RSTV. Note that line segment AB, line segment BC, and line segment AC are chords of central point O, and that line segment RS line segment SD and line segment TV are chords of central point Q. Quadrilateral RSTV and triangle ABC are cyclic polygons.
Theorem 6.2.1. If a quadrilateral is inscribed in a circle, the opposite angles are supplementary. So to prove this theorem, we can use the figure 6.23, where this figure given as quadrilateral RSTV is inscribed in circle Q. So we will to prove angle R and angle T are supplementary or no. So to prove this theorem, we can use the section 6.1 that an inscribed angle is equal in measure to 1/2 the measure of its intercepted arc, because measure of angle R equal to 1/2 measure of arc STV and measure of angle T equal to 1/2 measure of arc SRT. It follows that measure of angle R plus measure of angle T equal to 1/2 measure of arc STV plus 1/2 measure of SRV. So can be 1/2 parenthesis measure of arc STV plus measure of arc SRV, because arc STV and arc SRV form the entire circle. So measure of arc STV plus measure of SRV equal to 360 degree. By substitution, measure of angle R plus measure of angle T equal to 180 degree. So, by definition of supplementary, angle R and angle T are supplementary. So, this theorem is proof. Definition: a polygon is circumscribed about a circle if all sides of the polygon are line segments tangent to the circle. Also, the circle is said to be inscribed in the polygon. To clarify this definition, we can see the figure 6.24. So, to part A, note that line segment AB, line segment AC, and line segment BC are tangents to the circle D. And for part B, note that line segment MN, line segment NP, line segment PQ, and line segment QM are tangents to the circle T. Theorem 6.2.2. The measure of an angle formed by two chords that intersect within a circle is 1/2 the sum of the measures of the arcs intercepted by the angle and its vertical angle. To prove this theorem, we can use the figure 6.25, where this figure given as chords line segment AB and line segment CD intersect at point E in the circle O. And we will to prove this theorem whether measure of angle 1 equal to 1/2 times measure of arc AC plus measure of arc DB. So to prove this theorem, in the first step, we should to draw line segment CB in the figure. So this figure can be like part B. So from this figure, we know that measure of angle 1 equal to measure of angle 2 plus measure of angle 3, and measure of angle 2 equal to 1/2 measure of arc DB, and measure of angle 3 is 1/2 measure of arc AC. By substitution, we get measure of angle 1 equal to 1/2 measure of arc DB plus 1/2 measure of arc AC. Finally, the form can be measure of angle 1 equal to 1 over 2 times measure of arc AC plus measure of arc DB. So this theorem is proved. Theorem 6.2.3. The radius or any other line through the center of a circle drawn to a tangent at the point of tangency is perpendicular to the tangent at that point. So to prove this theorem, we can use figure 6.27, where this figure given as circle O with tangent line AB, where point B is the point of tangency. And we will to prove this theorem whether the line segment OB perpendicular to line AB or no. So the proving is circle O has tangent line AB and radius line segment OB. Let's see, name any point on line AB. Now we have line segment OC greater than line segment OB because C lies in the exterior of the circle. It follows that line segment OB perpendicular to line AB because the shortest distance from a point to a line is determined by the perpendicular segment from the point to the line. Theorem 6.2.4. The measure of an angle formed when two secants intersect at a point outside the circle is 1/2 the difference of the measures of the two intercepted arcs. So to prove this theorem, we can use the figure 6.31, where this figure given as secants line segment AC and line segment DC. And we will to prove whether measure of angle C equal to 1 over 2 times measure of arc AD minus measure of arc BE. So to prove this theorem, in the first step we should to draw line segment BD like this figure to form triangle BCD. Then the measure of the exterior angle of triangle BCD is given by measure of angle 1 equal to measure of angle C plus measure of angle D. So the form can be measure of angle C equal to measure of angle 1 minus measure of angle D, because angle D and angle 1 are inscribed angle. Then measure of angle 1 equal to 1 over 2 measure of arc AD and measure of angle D equal to 1 over 2 measure of arc BE. So measure of angle C equal to 1 over 2 measure of arc AD minus 1 over 2 measure of arc BE. So the form can be like measure of angle C equal to 1 over 2 times measure of arc AD minus measure of arc BE. So this theorem is proved.